Welcome to this video that I'm going to use to explain to you an application of derivatives known as related rates. Now, in order for us to get through this, we have to understand the notation of calculus and some of the things we've already done before. One of those is the importance of implicit differentiation. And we need to be able to interpret what this symbol dy over dx means. So dy over dx we know is slope in the context of taking the derivative. The reason it's slope is because the dy we've uncovered earlier, that actually means the change in y divided by the change in x. So change in y over change in x is the concept we refer to as slope. Well, we're just going to extend that understanding to some other quantities. So for example, if I had dv over dt, given that v is volume and t is time, then this would be interpreted to mean the change in volume divided by the change in time, which is interpreted as the rate at which the volume is changing. So if you were reading a problem, you'd be looking for something along the lines of the volume is changing at 3 cubic centimeters, that's volume, per second. That would be an example of a dV over dt, change in volume with respect to time changing. Oops. Now, moving on to what we're going to do with these problems is we're going to learn how to take the derivative of relationships. Now, these relationships are going to be typically some kind of mathematical formula. And suppose that we had this expression, and I wanted to take the derivative with respect to w. That means I want d something over dw. Now you'll recall from earlier implicit differentiation, if I just put something easy here, x squared plus y squared equals, let's say, 5. If I take the derivative with respect to x, that means 2x. Well, when I take the derivative of x with respect to x, that turns out to be a 1. So that doesn't even appear in our derivative. However, when I take the derivative of y, because y is obviously not the variable x, then the derivative of y with respect to x is dy over dx, and then the derivative of a constant is 0. Well, if I wanted to take the derivative of that same expression, x squared plus y squared equals 5, I could take the derivative with respect to y instead. Now it would be 2x dx over dy plus 2y, but now when you take the derivative of y with respect to y, that's just a 1, so that doesn't appear, and you'd end up with 0 on the right side again. So essentially, whatever derivative you're differentiating with respect to, the one on the bottom, if you come across one of those variables, you don't need to put the little, we call this a differential, this thing here, that's called a differential. You won't need that when you take your derivative. So if I look at this formula and I take the derivative with respect to w, well, the letter p, it would be dp over dw equals twice dl over dw plus 2, well, the derivative of w with respect to w, that's just a 1. If I took that same formula and differentiated it with respect to p, the derivative of the variable p with respect to p would be a 1. 2, now you take the derivative of L with respect to P, plus twice the derivative of W with respect to P. Well, if I took that same formula and now differentiate with respect to T, which is neither of these three variables, I just have to do my differential each time. So it's going to be dP over dt equals twice, take the derivative of L with respect to time, plus 2 dw over dt. Now, assuming that this is perimeter equals twice the length plus twice the width, which is how you get the perimeter of a rectangle, we should be able to interpret what this last one, not so much these first ones, this last one will be in line with how we're going to do most of these application problems we're going to run into. This would mean the rate at which the perimeter is changing as time passes. This would mean the rate at which the length is changing as the time passes. This one would mean the rate at which the width is changing as time passes. So I've got three formulas here, three common ones. First one is the area of a circle. Second one is Pythagoras' theorem. Third one is a formula we would use to get the volume of a cone. I'm going to take the derivative of each one of these formulas with respect to time. And when we do these related rate problems, we're always going to be differentiating with respect to time. So that's dt. All right, so area is a variable, so the derivative of area with respect to time is dA over dt. I have a constant, so pi just stays there. I take the derivative of r squared, so that's 2r, and then I need to finish it off my chain rule. Remember, we treat it like a chain rule when we do these implicit derivatives. So it's 2 times r, take 1 off your exponent, which I did, and now you take the derivative of the r, which would be dr over dt. dr over dt would be the rate at which the radius is changing as time passes. dA over dt would be the rate at which the area is changing as time passes. The next one, Pythagoras' theorem. So it would be 2a dA over dt plus 2b dB over dt equals 2c dC over dt, where A, B, and C are the three lengths of the sides of that particular right triangle. Now this one you have to be careful because you have r squared h multiplied together, which means when we take the derivative we would have to use the product rule. So volume equals, again you can just leave any constants out front. Now you take the derivative of the variable part, which I have here, so it's derivative of the first, 2r dr over dt. So derivative of the first, multiply that by the second, plus the first. Now I need the derivative of the variable h with respect to the variable t. That would be dh over dt. Oh, I forgot to take the derivative of the left side. So the derivative of volume is dv over dt. So that would be the rate at which the volume is changing as time passes. That would be the rate at which the radius is changing as time passes. And this would be the rate at which the height is changing as time passes. And the way these problems are going to essentially work is we're going to be able to substitute something for every one of these rates of change except for one. So for example, this is a common one with a cone-shaped container. Let's say you're pouring liquid into a cone-shaped container and you know how fast the height is changing and you know how fast the radius is changing. Well, if you knew that number and you knew that number and you could fill in these values for radius and height that would likely show up somewhere in the question, then you should be able to find the rate at which the volume is changing. Or if you knew the rate at which the volume was changing and they told you the rate at which the height is changing, well then you should be able to figure out the rate at which the radius is changing. And that's why they call them related rate problems. You want to be able to figure out as one quantity is changing, what effect is that having on other changing quantities in the same question. Alright, let's jump into a few examples. So we've talked about this notation a fair bit, so they've got a nice easy one that starts here. And they talk about a circular doggy puddle is growing at a rate of 12 square centimeters per second. So as soon as I look at this, I know that square centimeters is a change in area as time passes. This would be dA over dt. The question says, how fast is the radius growing? That's the rate of change in the radius. It's asking me to find dr over dt. Now, in order for me to do this, what I need to find is a relationship that connects these two differentials. So I need a formula that connects A, area, and radius. And we're talking about a circular doggy puddle. So this is kind of, if you're a checklist kind of person that says, try and figure out the changing quantities, maybe with the aid of a sketch. This one, I don't know if a sketch would help a whole lot. There is one down below. We'll get to it in a second. Write down an equation that relates the changing quantities. So in this one, I'm looking for an equation that equates area and radius. We'll get to that in a minute. You're going to take the derivative of both sides with respect to t, time, and then you're going to go through the whole problem, and you're going to, I don't know, that's more of a rearranging thing. You can usually jump right to this last one. Start filling in the given values, and you should have all the information except for one piece of data in the problem. So here's the sketch of what we're dealing with right now. And we're talking about the area of this circular puddle is changing. So I know dA, dt. Positives and negatives become important here because sometimes quantities are increasing, sometimes they're decreasing. If they're increasing, they're positive. If they're decreasing, they're negative. So this time the puddle is growing, the circular puddle is growing at a rate of 12 square centimeters per second. So this would be 12 square centimeters per second. The question asks me to find dr over dt. So as that circle expands out this way, the radius is changing, so is the area of the circle. So I need a formula that connects area and radius. Well, luckily for us, there is a nice formula that is used to find the area of a circle, that is pi r squared. And look at the two quantities in this formula, a and r. So once you've established a connection between the two changing quantities, the area and the radius, you take the derivative. So I'm going to take the derivative, dA over dt equals 2 pi r dr over dt. This is the one we're trying to find. So that means I need to substitute something for dA over dt. Well, there it is right there. I'm going to put a 12 in its place. And I need to also put something in for the radius. So in this case, it said in the question, and it'll usually tell you this in the question, this one said find this rate of change the instant the radius is equal to 10 centimeters. So there's my r value. You do got to watch for units. We're fine here though. Square centimeters, centimeters. I'm going to fill in now my changing quantities. So dA over dt, 12. 2 pi, it said when the radius is 10, that will equal dr over dt. So now to get the change in radius as time passes, I will take 12, get this product, so that's 20 pi. That will equal, that will equal my change in radius with respect to time. Now radius, when you have to put units on your answers in these. So I'm just going to grab my calculator here. So we need 12 divided by 20 pi. And I get 0.191. So dr over dt is 0.191. Now, we just need to put some units on this. So because it was in square centimeters per second, well, radius wouldn't be square centimeters. Radius is measured in just linear centimeters. The time frame will have to match up with the rate of change you used here. So it would be 0.191 centimeters every second. Now, one thing that's really, really important when you start doing these problems is you never substitute a quantity that is changing until after finding the derivative. So for example here, the 10, which represented the radius of the puddle, anytime a student does this, I always ask one simple question. So is the 10, that measurement, the whole question? If it is, you're allowed to fill that number in before you take the derivative. If it's not that measurement, the whole question, you must wait until after you take the derivative, because then after you take the derivative, you're dealing with rates of change, dr, dt's, and then you can do your substitutions. Okay, let's try another one. This one's talking about Joey, who's up on this ladder. It's 10 feet long. He's leaning against the back wall of an apartment building. when it starts to slide down the wall at 4 feet per second. So you can see they got a diagram set up here with a ladder. So the length of the ladder is 10. It's never going to change. So that number can go into your diagram right away. Now, as the ladder starts to kick away from the wall this way, right, and it says that his buddy here is standing 6 feet away from the wall, that means that this original distance is going to change. So I need a variable on it. They've called it x. And then this distance here is also going to change because the ladder is going to start sliding down this way. Now, they've given me one rate in the question. It says it starts to slide down the wall at a rate of 4 feet per minute. So the top of the ladder is coming down the wall. So that I've called that variable w. So dy over dt is going to be 4 feet per minute. Now, the one thing you got to watch for, and I mentioned it on the last slide, is you got to pay attention to positives and negatives. The rate of change in y with respect to time. Here's y. What's going to happen to y as this ladder slides down the wall? It's going to get smaller, which means y is a negative rate of change because that quantity is decreasing. Just looking at this question, so as x changes, it should come out in the end to be a positive value. So I need to somehow connect together here x and y. Well, if you look at this diagram, we're assuming the wall's at a right angle. We've got x, y, and 10. It's a perfect setup this time for Pythagoras' theorem. So let's go x squared plus y squared is equal to 10 squared. Now again, I can put the 10 there because it's 10 all the time. The length of the ladder is never going to change. Let's take the derivative. So 2x dx over dt plus 2y dy over dt. This is a constant. The derivative is 0. Now, I know dy dt, so I have a substitution for this one. I'm going to put negative 4 in its place, but I'm trying to find this one, dx over dt. So in order for me to find that one missing quantity, I need to fill in something for x, y, and dy dt. In the question, there should be enough information for us to figure all of this out. Lou is standing on the wall 6 feet away from the wall, so when it wants to know how fast is the base of the ladder moving when it hits Lou. So when it hits Lou, look at x. So the ladder's going to be, it's going to look like this at this point. So this is going to be 10. This measurement on the bottom at the very instant that they're talking about is going to be 6. So now I know x equals 6. So what we have is we want the rate of change at this very instant. When x is 6, the hypotenuse is 10, I still need y. But if I know that this is 6 and this is 10, I should be able to figure out y using Pythagoras' theorem. So y squared should be the hypotenuse squared, which is 100, minus the other side squared, which is 36. That's 64. So that other side's got to be 8. So y is going to be 8, x is going to be 6, and dx dt is going to be minus 4. So let's fill those all in now. 2. So you got to keep track. You got to make sure your diagrams are well labeled, so you know which side's x, which one's y. That's really important. X is 6 at this instant. Dx dt is our unknown. Twice y, which is 8 at this particular instant, and then dy dt is negative 4, and that will equal 0. This is going to give us negative 64, and this will be 12. So 12 dx dt. Take this to the other side, I'm going to get a positive 64. Dx dt will be 64 over 12, which is equal to 5.333. Now we need units, so it'll match up with this rate, so it'll have to be in feet per minute. So that's how fast the ladder is going to be going at the instant it hits his foot, which is the instant x is equal to 6, y is equal to 8, and of course the ladder cannot change length, so it's always 10. So those are a pretty basic introduction to related rates, and that's involving, in that case, Pythagoras theorem. So that one involved Pythagoras theorem. The prior one involved just a basic area formula. Let's see what my next one is here. So this next one's talking about pumping air into a spherical shaped balloon. So you got a balloon shaped like a sphere, a ball. And just looking at units, you should be able to tell me that this is the rate of change of the volume. So dV over dt, we're pumping air into the balloon, so it's increasing. So it's a positive 100 cubic centimeters every second. Determine the rate at which the radius of the balloon is increasing. So the rate at which the radius is increasing. So here's your radius. So what they're asking us to find is the rate of change in the radius with respect to time, dr over dt. And they want that rate when the diameter is 50. Well, the volume of a sphere, don't worry if there's any of these formulas you don't know. I always give you all the formulas. Now, if you're at home, you could look them up if you had to, but the volume of a sphere is 4/3 pi r cubed. Well, that's a perfect formula because it connects volume and radius. So all I have to do here is take the derivative, so dV over dt. I have a constant, 4/3 pi. Take the derivative of r cubed, that would be 3r squared. And again, we're differentiating with respect to the variable t, so I need a dr over dt. This is given, dV over dt, so that's 100. 4/3 pi times 3. So in order for me to get this measurement, the only thing I need is to know what's the radius the instant that they would like the rate of change in the radius. And it's the instant the diameter is 50. So if the diameter is 50, that means the radius is half of that, which would be 25 centimeters. So 25 squared. I just had a quick look there to make sure the units match up, and we're fine here. Centimeters, cubic centimeters per second. Sometimes what might happen is you'll get cubic centimeters per second, and then this measurement may show up in meters, and you'll have to convert this to match this rate of change unit. Dr dt is my unknown. Okay, so now this would be a matter of rearranging. So I'm going to have to go 3 times 100 and then divide by 4 times 3, so 12 pi times 25 squared. And this will give me then dr dt isolated by itself. So if I throw that into my calculator, 3 times 100, 300 obviously, divide that in brackets, 12 times pi multiplied by 25 squared. Make sure you put your whole denominator in brackets when you divide by multiple factors down there. And that will give me 0.013, and this would be in centimeters per second. And that would be the rate at which the radius of this balloon is changing. So imagine, as the air is being pumped into the balloon, it's expanding out this way. And as that happens, your radius is changing. Now, it's not changing very quickly, though, but at that particular instant anyway, once it's 25 centimeters of a radius, the rate of change at that particular instant is only 0.013 centimeters every second. What do we got here? We got a rock thrown into a pool of water. A circular wave leaves the point of impact and travels so that its radius increases at 25 centimeters per second. So radius increases at that rate. Well, that's dr over dt is 25 centimeters per second. So imagine a rock is thrown into a pool. So the rock hits the water and it makes a wave, a circular wave. It's a bad circle, but you get the idea. And the radius of that will change. It wants to know, as that wave is going out and the radius is increasing at this rate, what's the impact it's having on the circumference. So it wants change in circumference as time passes. So I need a formula that connects circumference and radius. Well, fortunately for us, there is such a thing. Circumference is equal to 2 pi r. Take the derivative. Change in circumference as time passes. Constant 2 pi. Take the derivative of r. dr over dt. So this was given, dr dt. So the change in circumference as time passes is 2 pi. dr over dt is 25. Keep hitting that with my hand, sorry. Is 25. One thing you'll notice here is the 1 meter didn't get used. What that simply means is that it doesn't matter. It just means that the radius travels out at the same rate regardless of where the wave is. Now, of course, we know that with friction and all kinds of stuff, that's not what it really will happen. But ignoring all of those scientific facts, the math behind it says this is what should happen. And then, of course, this would just be, I'm just going to leave it, dc over dt. So 2 and 25 is 50 pi. Circumference would be measured in centimeters every second. So the time here will always match up with the time over here. So that was a pretty easy one, straightforward. Okay. Next one involves a cone-shaped tank or container. These are really common questions. They're a little bit more difficult, so pay close attention to this one. So it says a water tank has the shape of an inverted circular cone. This is what they mean by that. Kind of like a paper cup you'd drink out of a water fountain. So like that. And it says it's being filled with water. So water's being poured in to that at this particular rate, 2 cubic meters every minute. So the change in volume with respect to time, and again, paying attention to units, you can often tell what your measurements are rates for. So this is the change in, that's cubic, that's a bad 3, cubic meters per minute. Now the actual water tank has a radius, so this is fixed, this doesn't change, this is the tank, has a radius of 2 meters, and the height of this container is 4 meters. Now the water, so imagine as water's being poured into this, there's things that are going to change. So the depth of the water is going to change, I'll call that H, and as the water rises up through and gets closer and closer to filling, then imagine inside there's another cone of water. Well, the radius of that cone of water is going to change. Things that are changing, you need to put variables on. This is one, the most common mistake students make here is they put 3 where the H is. And again, I ask one simple question. So is it going to be 3 meters deep, the water, the entire problem, or is it going to change? And students will say, well, no, it's going to change. As you pour water in, it's going to change. Things that are changing, do not ever substitute until after taking the derivative. Okay, so I need a way to connect together here volume, because they're asking me, I didn't finish reading here. It says find the rate at which the water level is rising. Water level is rising would be the H. So what they're asking us to figure out is dH dt. So the only connection I have between volume and radius and height is this formula, which we looked at earlier. It's the volume of a cone is 1/3 pi r squared multiplied by h. However, this problem generates a further step that we haven't had to encounter yet. And the problem here is that there are 1, 2, 3 variables. So if I was to take the derivative, I would get a dv dt, I would get a dr dt, and I would get a dh dt. Unfortunately, there's not enough information given in the problem for me to handle 3 variables because they only gave me one other differential. So they gave me dv over dt, but I wouldn't have the dr over dt to let me find dh over dt. So we need to figure out a way around that. And the way we do it is using what's called similar triangles. So I'm going to go back over here to the container and say, well, I wish I could get rid of the variable r. And we're going to do that. We're going to take a comparison between the water So here's the water, and I'm just going to draw a cross-section of the right side. So this is a two-dimensional cross-section of the water, where you've got radius and height. I'm going to compare that with in this case, the tank. So the tank, if I do a cross-section, it would be 2 meters across the top and 4 meters down this way. Well, the triangle inside, this little angle in the bottom and this little angle in the bottom are the same because it's the same angle. It's this one here. This one has a right angle at the top of the water. If I went up here and across here, I also have a right angle. Well, by default, this angle is also the same. So that's what we refer to as similar triangles. So at some point in your schooling, you would have learned that similar triangles have their sides in what are called corresponding ratios. Meaning if I go r, this measurement, over 2, I should get the same thing as h over 4. What we now do is rearrange this to get what r equals. So I'm just going to cross multiply here. 4r equals 2h. Get the r by itself. So I can see here that the radius, 2/4, is the same as 1/2 h. So instead of putting the variable r, notice I'm doing all this before taking the derivative, I'm going to substitute 1/2 h in there instead of r. So I'm going to keep the formula the way it is. Volume equals 1/3 pi. Instead of r, I'm going to put 1/2 h because that's what the radius is equal to. And now I'm going to clean this up. Again, you always want this to be as simple as possible when you go to do your derivative. So v is going to equal, so when I square a half, I'm going to get a quarter. Multiply by that 1/3, I'm going to have 1/12 now. Pi, h squared times h. So I've got a new formula, but look at the advantage of this new formula. It no longer has the variable r in it. So I'm down to a scenario that has just two variables, and I know dv dt. Therefore, if I take the derivative, I should be able to now figure out dh dt. All right, so here we go. Take the derivative of the left side, dv over dt. 1/12 pi is all just constant. Take the derivative of your variable then, 3h squared. Finish off your implicit derivative with dh over dt. Oops. It says to us, oh, this is a pi, not an h, sorry. 1/12 pi, there's your constant. Now your derivative of h cubed is 3h squared dh dt. Alright, so we're given dv dt. It's positive 2 because you're adding volume. So this is positive 2. 1/12 pi 3, and it says in the question to find the rate of change the instant the water's 3 meters deep. Well, with the water's 3 meters deep, they're telling me h. So at that particular instant, we want the rate of change is the instant that the water is 3 meters deep. Well, that's going to leave then one unknown, dh over dt, which is the rate at which the water level is changing. Now I need to get that by itself, so I'm going to multiply by 12, so 24. Divide by 27 pi, and that should leave us with dh over dt. Throw that in a calculator. We'll get the right units on it at the end. 24 divided by, again, make sure you use brackets, so it'd be 27 then times pi as my denominator. .283. And I would be in, let's see my units here, I gotta look things over. Meters, cubic meters per minute. So the height of the water, I'd measure it in linear meters. So I'm gonna be in meters per minute. Okay, I'm gonna do one more question as a sample, and this is one involving shadows. So there's two types of shadow questions. I'm going to do one of them. You could use this kind of as a template for the other one. This one is a situation where the light is up on a post and the person's underneath it. So in this question, you've got a lamp post with a light up here. There's your light. There's a person who's standing down here somewhere. And what happens is the light shines, right? The light shines. The person blocks the light, so then what happens is their shadow gets cast on the ground down here, kind of at this angle, getting blocked out because of their body. And let's see what they tell us. So the lamp post is 20 feet high. Well, the height of the lamp will never change the whole question, so that's 20 feet. The man is 6 feet tall. His height will not change. Remember, things that are not changing, you're allowed to put on your diagrams. Things that are changing, you must use variables. So this is a shadow, so I'm just going to call it X. So as he moves toward the lamppost, so he's going this way, the rate of which is shadows, the length of the shadow is going to change. Well, so is the distance between him and the lamppost. So I'm going to call that measurement Y. So on this diagram, I somehow need to connect together my X and Y. Well, to do that, we're going to use similar triangles. So there's the big triangle, right? The big triangle in this question looks like this. This is 20, and the bottom of it is, well, it'll be Y plus X, I guess. So this is 20. This piece down here is Y plus the little piece in the front triangle is Y plus X. And then you've got your smaller triangle with a shadow where it's the man standing here who's 6 feet, and then out in front of him is an X. Is an X, like so. Well, like we used last question, I'm going to use similar triangles because this is a right angle, and this is a right angle. This angle is the same angle in both diagrams, right? It's this one in the corner, which means by default, this has to be the same. So this time I'm going to say 20 over 6 has to equal Y plus X over X. I'll cross multiply and tidy this up. So 20x is equal to 6y plus 6x. Let's move the x over. So 14x is 6y. Oh, I forgot earlier on. So what rate did they give us? The man's walking 5 feet per second. So that means that if he's going this way, the distance between here and here, so they've told me dy over dt. Now watch this though, this is really important. It's negative 5 feet per second. You say, well, why is it negative? It's got nothing to do with left or right, up or down. That's got nothing to do with it. It's increasing and decreasing. So as this question unfolds and this man walks this way, right, toward the lamppost, y is going to get smaller, which means you need a negative rate of change. So over here, we're all set to take the derivative. So it's 14 dx over dt, which is the rate at which the shadow length is changing. That's what I'm trying to find. Equals 6 dy over dt, which is given in the question. So just fill that in. 14 dx dt, 6 times negative 5. So dx over dt is negative 30 over 14, and that would be 2.143. It's negative, which means the shadow's getting shorter. Negative 2.143 feet every second. So in this case, his shadow's decreasing at 2.143 feet per second. A lot of times with these ones, they'll ask a secondary question. Now they've kind of put it first, but you'd have to do the second part here first. It says, at what rate is the tip of his shadow moving? In this scenario, you've got to now factor in, because the man, so the shadow is decreasing at 2.143 feet per second, so it's getting shorter, so it means it's coming this way. But at the same time that's happening, the man's also still moving. So when you put that all together, the shadow is moving at, well, it's always moving at the rate the man's walk, because your shadow moves with you. So it's going to move at the 5 feet per second. But at the same time that's happening, remember the head of the shadow is getting shorter, so it's actually moving in this way. So it's actually going to be going at 2.143 seconds, or feet per second. So you got to combine those two together to say, well, the shadow in total is traveling at 7.143 feet per second. Okay, so there's a good sampling of some related rate application type problems. I've got 3 of them on here that are in your notes, and then I have my answers following. We'll discuss these probably in class one of the days, but if you'd like to try a few on your own, here would be 3 good examples. Now these are 3 fairly challenging ones, so you have to have a pretty good handle on how these things work before you start into these. So you might want to go to your practice questions first, get some confidence going before you try these 3. I don't want you to get discouraged too early, but these are a little bit more challenging. Alright, so thanks for watching this video, and it's really important now that you put some time into practicing these related rate problems. Again, there's no way I can do a sample of every type of problem you're going to run into. That's what problem solving is all about. So you need to now develop a skill set that will let you manage any type of related rate problem now that you understand the notation and the strategy that we're going to use to solve these problems. Okay, so best of luck with these, and reach out if you have any questions. Thanks for watching.